Hi, I'm Ryan Blanchard.
And I'm Emanuel Manco, and this is our variable switching buck power supply. This is the main screen. It's our logo. We're going to start with the keypad. So the user is able to input any voltage between 0 and 30 volts, and this includes one decimal value. So one example would be 2.5 volts. You enter it, and you're able to see it on the voltmeter, and you can also see it on the screen. Some of the values are a little less accurate because of the way the meters are connected, but they're pretty close to where we want them to be. So my board is using a PIC 24FJ256 DA210 chip with a graphic accelerator in it, and is using an SRAM as buffer. This is an asynchronous SRAM with a 10-second access time. The chip is using an external 8 MHz oscillator, which is multiplied by 4 internally for a 32 MHz clock. The graphic accelerator itself is using 96 MHz, which allows the user to use the screen without affecting any of the analog to digital converters, as well as the serial output to the DAC. The second one we're going to show is the round dial. So the user is able to change the value coming out constantly without having to just input different values into it. Next, Ryan will talk about the Ryan will show the max. Go to the keypad. That is the max value that you can output. So this is the board for the digital interface. Here we have the main processor, the PIC for microchip. The 512 megabyte SRAM is located over here, and this is the 8 MHz oscillator. The board is protected from any power surge with the 2 voltage regulators, one 5 volts and one 3.3 volts. The 3.3 volts is used to power up the chip and the SRAM, and the 5 volt one is used to power up the LCD screen with a resistive touchpad. Here is the DAC that outputs any voltage to the analog part that Ryan made based on any digital input that is put to the screen, and the serial data is going from the chip to the DAC to output any voltage that we need.
Ready? Alright, we're going to start off talking about the analog portion of this project now. If you look, we have the actual supply plugged into this Variac, which is at 100% right now, and plugged at 120 volts. And that runs to this transformer that we have on the inside right here, which steps it down by a factor of 1/3 and outputs a voltage of around 54 volts because we have the input of 169 because 120 is the RMS value. So I have this power resistor down here, step it down to 50 volt input because that's what I did all my calculations for. And the transformer was a little bit off from that, so I wanted to get what I wanted to get, so I used that. And then if we look at this circuit here, this displays my use of voltage regulation throughout the entire circuit. I have a Darlington diode here, and this is a 15.5 volt Zener diode that I have from the base to ground, and then I have this 4.7 over here, and then from that I have all the different voltage regulators throughout the entire circuit, and that is right here in the actual circuit itself, and that would be the diode, and this would be my 12 volt, a 5 volt, and we have it says 9 volt on there, but it actually puts out 7.3 because we changed it because it's a variable supply to give his board a better value for what he needed, because we originally thought it was higher than what was necessary. From there we can look up here and see the high side MOSFET, and then we have the low side MOSFET here. Only one is on at a single time, or else we'd have shoot through, but that doesn't happen because we have the LT1339 here controlling the gates of each, and it outputs the exact opposite to each individual gate, so one will never be open at the same time as the other. therefore we prevent shoot through. And here's my inductor that I have, it's 41 microhenries. And then we have these 4 caps on the output in parallel to add to a total capacitance that I need, but they're in parallel like this to prevent the ripple current from causing any of them to blow, because each individual electrolytic cap like that has a built-in ESR that we need to account for, and that's why they're in parallel like that, so we can be safe. And right here we have a switch that turns the load on or off and then back on, and maybe you can't really see it, but this is just a simple voltage divider I made to take the output down from a factor of 1/10 to send it to the board, because outputting his max is 3 and we output 30, so take that out by 10 and that puts it in his range, and then you put a 3.3 volt linear diode in parallel with the load so we can't damage his board, and that works out pretty good. And that's and the last part we need to look over on the analog portion is over here. This is the basic drawing before we look at it on the inside of the feedback loop I have. So we have 3 resistors here, the voltage input from the microprocessor, and a 1.25 volt that's output by the feedback pin of the LT3039. Then we have the final output that we want to get here. So by changing this value from 0 to 3, as we showed you earlier in his video, we changed the output of the actual supply, and that goes in right here with this op amp that has a unity gain buffer, and then it all works. So if you output a 0 from this, we get a 30 out over here. You put out output of 3, we get 3 volts, and everywhere in between we used a bunch of data points to get a line of best fit, and that's how we got the numbers we showed you earlier.